Balancing equations. To write a balanced chemical equation, first write the skeleton equation. Then we will use coefficients in front of each element or molecule or compound to balance the equation so that it obeys the law of the conservation of mass. Here's a balanced equation for making a bicycle. Maybe this will help you visualize it. The numbers are called coefficients. And let's see where we have a number. Right here. See the 2 over there? See the 2 over here? They are small whole numbers, integers, that are placed in front of the formulas in equation in order to balance it. So you have the same amount of fluorines, for example, on the left that you have on the right, or in this case, bicycle parts. Okay, so let's do bicycle parts. I said this was fluorine. It's not. It means frame. So we have one frame. We have 2 wheels. We have one set of handlebars, and we have 2 pedals. We put them all together, they react. There's our arrow. So here's your reactants. Just write an R there. And here's your product. And what do we have? We have one frame. There's one F. We have 2 wheels. We have one handlebar. And we have 2 pedals. And you'll notice on each side we have the same amount of frames, wheels, handlebars, and pedals. And that's due to the conservation of mass. We'll now leave the bicycle repair shop and talk again about chemistry. So we're going to use the reaction we've been dealing with, which is methane plus oxygen yields carbon dioxide plus water. You can see we've written to the right, they're all in the gaseous state. And now we're going to break apart each molecule and see how many elements we have. So for the CH4, we have 1 carbon, 4 hydrogens. We have 2 oxygens, 1 carbon, 2 oxygen, 2 hydrogens, and 1 oxygen. When we balance equations, we're going to put whole numbers, positive integers, in front of each molecule or each element so that on the left side, the reactants, we have the same amount of carbon atoms, hydrogen atoms, oxygen atoms, whatever, that are on the right side. Mass is conserved. Let's balance our first equation. This is going to take some practice so you can learn the tricks to do this. So let's just start off. We have methane plus oxygen again yields carbon dioxide and water. So what do we have over here? Let's not look at this 2 over here and this 2. Let's just pretend they're not there for a second. On the left side, you have 2 oxygens. Again, ignore the whole number in front. On the right side, you have 1, 2, 3. So I need more oxygens. So the first thing I'm going to do is multiply this by 2, and you can see the 2 there in the circle. So that now gives me 4 oxygens. Okay, that's pretty good, but I only have 3 on the right side. How can I make that equal 4? Well, that's where this 2 comes in. So now I have 2 oxygens, a total of 4 oxygens. I have 2 there and 2 there. So that's good. 4 oxygens on the left, 4 on the right. Let's see if that solved the problem for us. 1 carbon on the left, 1 carbon on the right. 4 hydrogens on the left, and let's see. How about that? 2 times 2, I have 4 hydrogens, so it all checks out. Those numbers, those 2 2's we put in, those are called coefficients. Your equation is now balanced. Mass is conserved. Here's our complete equation. And again, you see the gas, and you see the 2's we put in. Okay, those are the coefficients. They tell the number of representative particles, which can be atoms, molecules, or formula units. And all the coefficients do is they change the amount of compound or molecule. Subscripts indicate the number of atoms of each element in a molecule. If you change the subscripts, that would change the type of compound or molecule. So we're not going to be doing that. We're going to be changing the coefficients to balance the equations. Here's a nice way to look at using frankly, a physics illustration. We're balancing masses on either side of a point there, a fulcrum. We're balancing the torques, letting the torques equal 0. But that's for physics. Let's go to chemistry. If we look on the left side, if we just write it like this, which was our skeleton equation, we have 2 hydrogens as reactants and 2 chlorines. The product, though, there's only one hydrogen and one chlorine, so that's represented by this picture. You can see how it's weighted more to the left side. It is not balanced. Now when we balance it, we put a coefficient of 2 in front of the HCl, the hydrochloric acid, and now we have 2 hydrogens on the left, the reactants, 2 on the right, the products, 2 chlorines on both sides, and look how nicely it's balanced. And it wouldn't work with the physics because the masses are different, but this is a great illustration. That's why we call it balanced. We've just picture it as balancing on a fulcrum there. Write a balanced chemical equation for this reaction. We have chlorine plus sodium bromide gives you bromine and sodium chloride. First, write a skeleton equation. Chlorine is a diatomic molecule, so we write Cl2. Sodium has a valence of +1, bromine of -1, so that's how you write sodium bromide. Bromine, also a diatomic molecule, so it's Br2. And then sodium is +1, chlorine is -1, so there you go. That's your skeleton equation. Next, count up the number of each type of element on each side of the reaction. The reactants on the left and the products on the right. You won't have to do this every time, but for now it's a good formality to get you going. So chlorine, you have 2. Sodium, 1 bromine. On the right side, we have 2 bromines and 1 sodium down there and 1 chlorine. So does that look balanced? No, you have to have the same number of each element on each side. And here's where we take an art form that is balancing equations and trying to come up with some rules that make the art a little easier to do. So let's identify one element that is not balanced. It's best to start with an easy element. And by what we mean with easy element, the fewer places the element appears on both sides of a reaction, the easier it will be to balance. So let's look at this. Why are we choosing chlorine? Well, chlorine's here in one place, chlorine's over here. Sodium is over there next to bromine, and it's also next to chlorine. Bromine is next to sodium, and then it's by itself. So yeah, actually it's kind of a flip on this one, but we're going to choose chlorine. It's on the top. See how that goes. So we highlight it there, and then we move on to the next page. Identify the side that needs more of that particular element. Well, that's easy. We've got chlorine highlighted. We have 2 over here, and we have 1 here. So we circle this one. We have to do something to that chlorine on the right side. Now we can go from the table back up to our skeleton equation, and we identify which molecule or element needs an added coefficient. In this case, we're going to work with sodium chloride, salt, because that's the only product containing chlorine. To determine the coefficient, take the amount of that specific element that you need from the molecule. Okay, so we need 2, because there's 2 chlorines on the left, we need 2 on the right, and divide that by the amount of the element you have, which is only 1. So 2 divided by 1 is 2, and then put that 2 in front of the sodium chloride. If for some reason it's not a whole number, like 1.5, multiply all the formulas in the reaction by a whole number to make all the coefficients whole numbers. So if you had 1.5, multiply that by 2 to get 3. Again, this may look like a lot of work for a very simple reaction, but when you get more complex ones, it's good to have a roadmap like this to go on. Now, take a step back and see if we've fixed it. So we go back to our table, and we didn't change anything on the reactant side, but now let's go over here. Still have 2 bromines. And what did we do here? We have 2 chlorines, which is what we wanted, but it also multiplied the sodium by 2. So we have 2 there. So we will go to the next slide and see how we fix that one. Just take a look at it for a second. Maybe you can figure it out before we get there. And when you're ready, advance the slide. Well, I'm hoping you saw what to do. When we multiplied this by 2, we wound up 2 chlorines, 2 sodiums, and 2 bromines. You look to the left, we have 2 chlorines, that's good, but we only had 1 sodium and 1 bromine. How can we make them 2? Well, very nicely, the sodium bromide is standing all by itself, and if we were to put a 2 in front of it, See the purple 2? We now have 2 sodiums and 2 bromines. We didn't touch the chlorine. Okay, so that still just has 2, but look what we have. Everything matches. This may take more than one iteration and frequently will when you have a more complex reaction. But we now have a balanced chemical reaction.